Good morning and welcome to the last day of this fabulous International Congress. A brief history, very selective, of model theory and its applications to algebra, given by a student of Abraham Robinson's. Abraham Robinson spoke on this topic in ICM in 1950 in Cambridge, and in 1970 there was a great deal of excitement as we saw model theory applied to give us connections between the p-adics and power series over finite field by Ax, Cochin, and Yershoff. At the ICM of 40 years ago in Vancouver, Robinson was scheduled to give a plenary talk, but unfortunately died that spring. His topic was to be work with Peter Roquette on more connections and specifically bounds, using model theory to say something about number theory. 4 years later, Angus MacIntyre returned in his sectional talk at the ICM in Helsinki to discuss the Robinson-Roquette work. Over time, model theories continued to develop and to be applied within mathematics. After Alex Wilke's breakthrough result on the model theory of the reals with exponentiation in the early 90s, one hoped to see applications of this result in the same spirit as some of the things we had seen from other parts of model theory, this time using O-minimality. We had to wait a bit, but in the last decade, things have blossomed, and today's speaker has had a seminal role in this work. Jonathan Pila was born in Australia, did his undergraduate studies in Melbourne, then went to Stanford for his 1988 PhD under the guidance of Peter Sarnak. After a few years of postdocs, he returned home to Australia and for 10 years managed his family's textile manufacturing companies. Oh, no. He kept a hand in mathematics, fortunately for all of us, and as a trailing spouse moved to England to a position in Bristol early this century. While visiting Oxford, he encountered Alex Wilke, then the reader in mathematical logic there, and a collaboration began which led to the beautiful work and the hoped-for applications of the O-minimality theorems previously obtained by Wilke. Pila's contribution in his work has led to several prizes and awards bearing names such as Clay, Whitehead, and Karp. He is now the reader in mathematical logic at Oxford, and it is my great pleasure to introduce him to you today to speak about O-minimality and Diophantine geometry.
Okay, thank you. Thank you very much, Carol. It's a great honor to be invited here to address this forum. I'd like to thank the program committee and add my thanks also to the organizing committee for the wonderful organization of this Congress. So this talk concerns some recent interactions between model theory and Diophantine geometry. And in particular, it concerns a counting result about rational points on certain kinds of non-algebraic sets in real space and applications to certain Diophantine problems. But the wider context involves the model theory of exponentiation and its connections with both the problems and the methods. I hope to explain these connections and to bring out the pervasive presence of Schanuel's conjecture in transcendental number theory. I plan first to describe the evolution of the Zilber-Pink conjecture from the classical Mordell conjecture of 1922, proved by Faltings in 1983. Then I will describe Schanuel's conjecture and its functional analog, the Ax-Schanuel theorem. I will say a little bit about the model theory of exponentiation and its connection with the Zilberpink conjecture and with O-minimality. And then I will describe point counting in general and in the O-minimal context, moving towards some specific applications and problems. There are too many topics to cover in any detail, but my objective is to stress the ideas and their interconnections. So, Diophantine problems are an ancient and central part of number theory. In the first instance, they involve solving systems of algebraic equations in whole or rational numbers. Deciding whether an equation or a system has solutions or not is very difficult. As Manjul Bhargava mentioned in his talk, it is not known at the moment how to decide if an elliptic curve has a non-trivial rational point. The general problem is known to be undecidable for integer solutions. Finiteness is a more robust property. Mordell's conjecture, also described by Bhargava, is a general finiteness statement giving geometrical conditions for a curve to admit only finitely many rational points. Three innovations take us from Mordell's conjecture, now Folting's theorem, to a broad and very much open finiteness statement known as the Zilberpink conjecture. The first step, due to Lang in the 60s, recasts the statement to concern a subvariety of a group variety. I want to start with the very simplest example, which does not involve any rational points, and which appears in the pictured paper by Lang. So we consider an algebraic curve in the square of the multiplicative group. This is just the zero set of some irreducible bivariate polynomial in C star squared. We look for points on the curve whose coordinates are roots of unity, that is, they're torsion points in the group. The result says that there are only finitely many such points unless the curve has a very specific form which obviously gives rise to infinitely many such points, namely that the curve is a translate of a subgroup. And you can observe that if one coordinate of a point on such a curve is a root of unity, then so is the other one. And so you get, you get infinitely many points. Moving to higher dimensional multiplicative groups and subvarieties, the conclusion is that there are finitely many subvarieties of a specific form, cosets of multiplicative subvarieties by torsion points, that contain all the torsion points in our subvariety. The torsion points on such subvarieties are again dense in Zariski topology. And thus, in particular, there is a finite description in very specific terms of the set of torsion points in the subvariety, in other words, of the solution set of this Diophantine type problem. The results on this slide won't come up in the sequel, so we don't need to look at them except in a very expressionist way, but I wanted to reconnect with the Mordell conjecture, how it fits into this picture. If we replace powers of the multiplicative group by another kind of algebraic variety with a group structure called an abelian variety, a higher dimensional analog of an elliptic curve, we get the Manin-Mumford conjecture proved by Raynaud. And if we now replace torsion points by the division points of the finitely generated subgroup, we get Mordell-Lang. And as you see, these results have the same general form of a finite description in very specific terms. Mordell-Lang implies the original Mordell conjecture because a curve can always be embedded in its Jacobian, an abelian variety, as explained in the lecture by Mark Green. And the group of rational points of an abelian variety is finitely generated by the Mordell-Weil theorem, whose prototypical version was proved in the very same 1922 paper of Mordell. But the point for us is the shift in formulation. Mordell-Lang is about the interaction between subvarieties of some ambient group variety and certain distinguished subvarieties, namely its subgroups, and it posits a finite description. The second innovation, due to Andre and Oort, is to consider a wider class of ambient algebraic varieties, namely Shimura varieties, which are central objects in arithmetic geometry. I want to describe the formal structure of the conjecture before giving some detail on one example. A Shimura variety X comes equipped with a collection of special subvarieties which come naturally from its underlying structure, just as multiplicative subgroups are naturally associated with multiplicative groups. Special subvarieties of dimension 0 are called special points, the analog of torsion points. The conjecture concerns the interaction between a subvariety V of X and the special subvarieties, and it takes exactly the same form as before. The Andre-Oort conjecture remains open in general, though it is known under GRH and unconditionally in various cases. The simplest Shimura variety is the complex numbers, considered as the moduli space of elliptic curves parametrized by their J invariant. It is a classical and beautiful picture. As background, recall that the quotient of the complex numbers by a lattice has the structure of an elliptic curve. We may normalize the lattice to be generated by 1 and tau lying in the complex upper half plane and call the associated elliptic curve E sub tau. It is determined up to isomorphism by its J invariant. Assigning to tau the J invariant of E sub tau defines the modular function, or J function, on the upper half plane. It is a holomorphic function and invariant under the action of the modular group, which acts by Möbius transformations in the way shown. Further, for every rational 2x2 matrix G, the two functions J of tau and J of G tau are related by a modular polynomial. So that generalizes the modular invariance. If this matrix G is actually in SL2Z, then J of tau and J of G tau are just equal. The special points in C are the J invariants of elliptic curves that have extra symmetries, known as complex multiplication. And this happens precisely when the corresponding tau is quadratic over Q. These special points, the J of tau, are classically known as singular moduli, and they are algebraic numbers with very rich arithmetic, which we will come back to. And let's just observe at this point that rational 2x2 matrices preserve quadratic points. They take quadratic taus to quadratic taus. So here is a picture showing the classical fundamental domain for the SL2Z action in gray and its transformations under the modular group. Now, the André-Oort conjecture holds trivially for one-dimensional Shimura varieties like C, as there are no non-trivial proper subvarieties, only points. The simplest non-trivial case is the case of C squared, proved by André. The special points of C squared are the points for which both coordinates are special, that is, their singular moduli. Special subvarieties are, as shown there, they comprise modular curves, vertical lines on a special ordinate, horizontal lines on a special coordinate, special points, and C squared itself. And you can observe that all of these contain a dense set of special points. And for modular curves, this is because they come from a rational 2x2 matrix acting on the upper half plane. And so if one coordinate of a point on such a curve is special, then so is the other one. The André-Oort conjecture, here André's theorem, asserts that a curve in C squared containing infinitely many special points is special. It is the analog of the earlier result about torsion points on curves in C star squared. Now here briefly is a description of special subvarieties in C to the n. And they're basically a hybrid of what happens in C squared. You can set some coordinates to be constant and special, and you can relate various pairs of coordinates by modular relations. And there's a more general notion of weakly special subvarieties where constant coordinates don't have to be special. Other examples of Shimura varieties include moduli spaces of abelian varieties, and special points here are again CM points, the points with the maximum number of symmetries. But special subvarieties are quite elaborate to describe. André generalized the special point conjecture further to a wider class of mixed Shimura varieties, so-called, which include families of abelian varieties fibered over their moduli spaces. It takes exactly the same form. This gives ambient varieties in which the André-Oort, Manin-Mumford, and Mordell-Lang conjectures can all be formulated, but they are not implied by this conjecture because non-CM abelian varieties and their torsion points are not special. So one further innovation gives the Zilber-Pink conjecture, also known as the conjecture on unlikely intersections. It takes place in the same setting. One has a subvariety V of a suitable variety X. But instead of considering special subvarieties contained in V, we consider special subvarieties which intersect V in a set with a typically large dimension. They intersect too much. This is a generalization because to contain a special subvariety is indeed atypical in this sense. So you would expect equality in that dimension statement. That would be typical. The conjecture is again a finiteness statement that there are only finitely many maximal atypical subvarieties, even though there are infinitely many potential candidates. This idea has three independent sources in work of Zilber, Bombieri, Massazania, and most generally, Pink. Zilber was motivated by Schanuel's conjecture and his work on the model theory of complex exponentiation, on which a bit more shortly. The conjecture is open even for subvarieties of multiplicative groups. It implies all the conjectures mentioned so far and is the subject of active research on several fronts. The most complete result known is for curves in C star to the n, and its analog in an abelian variety in a somewhat weaker form. An atypical subvariety of a curve is either the whole curve, if it is contained in a proper special subvariety, or a point on the curve, which is contained in a special subvariety of codimension at least 2. So Zilber-Pink for curves may be stated as shown: if the curve itself is not atypical, then it has only finitely many atypical points, and that is points which lie in a multiplicative subgroup, in the multiplicative case of codimension 2. I want to turn briefly now to transcendental number theory. Major classical results include the Lindemann's theorem on the exponentials of algebraic numbers and the Gelfand Schneider theorem. Gelfand Schneider and others made various conjectures generalizing these results, but a concise, comprehensive conjecture was formulated in the 60s by Schanuel. The right-hand side n in this conjecture is optimal, since we may certainly have all the zi's algebraic, as in Lindemann's theorem, or all the e to the zi's algebraic. Schanuel's conjecture implies Lindemann's theorem, Baker's theorem, the 4 exponentials conjecture, and much more. It remains open even for n equals 2. For example, it is not known that log 2 and log 3 are algebraically independent. So this is the book. Schanuel's conjecture first appeared in print in this book by Lang. But Schanuel's conjecture has been proved for power series, the analog conjecture, and more generally in function fields by Ax. So on the right is Ax's paper proving the result known as Ax-Schanuel. So here is a version of Ax-Schanuel. For functions, the right condition on the functions, on the xi, is that they should be linearly independent over Q modulo constants. Because if some rational linear combination of the functions xi is a constant, then you get an algebraic relation on their exponentials too. So you could imagine if you added in xn, which was dependent in this way on the others, then the transcendence degree wouldn't go up because both objects that you added have relations. So I don't want to dwell on the form of this statement, which doesn't really concern us further, but I do want to observe a geometric consequence that will be important. We consider the coordinate functions on some algebraic subvariety of c to the n and their exponentials. So the coordinate functions on W are linearly independent over Q modulo C, just if they're dependent over Q mod C, just if W is contained in a translate of a proper rational linear subspace of C to the n, which we will call a weakly special subvariety in this setting. Ax-Schanuel in this setting implies that if W is not contained in a weakly special subvariety, then there are no algebraic relations on its image under coordinate-wise exponentiation. That is, its image is Zariski dense in C star to the n. This special case of Ax-Schanuel, which corresponds to Lindemann's theorem, I call Ax-Lindemann, and it will play a key role later. Reformulated, it characterizes the maximal algebraic subvarieties contained inside the inverse image of an algebraic subvariety under exponentiation. They are always weakly special. To see this, suppose that W is contained in the inverse image of V, and let L be the smallest weakly special subvariety containing W. Then by the first form, the image of W is Zariski dense in the image of L, which is algebraic, and so must also be contained in V. Okay, so turning now to model theory, there is not time here to introduce the basic first-order setup. A modern viewpoint centers on the sets which are definable in a given structure. For example, in the structure of the complex numbers as a field, one considers the subsets of C to the n that may be defined using individual complex numbers, the field operations, logical connectives and, or, and not, and quantifiers running over the complex numbers. An important theorem of Chevalley implies that any such set can be defined without quantifiers, and so the collection of definable sets is just the Boolean algebra on algebraic varieties. The first-order theory of C is very well behaved. In particular, it is decidable, largely because the definable sets cannot get too complicated. If we add the complex exponential to the structure, it becomes very complicated because the integers are definable in that structure, as in the way shown, and one then has phenomena associated with Gödel's theorem, undecidability of this structure, and its extreme complexity. However, Zilber showed that assuming Schanuel's conjecture and some further properties, a suitable non-first-order setting for complex exponentiation has a well-behaved theory. So that's all a bit by the way, but his work on exponentiation led him to formulate his CIT conjecture, which is the Zilber-Pink conjecture in this multiplicative setting. And to show that it is the difference between Schanuel's conjecture and a stronger uniform Schanuel conjecture which admits first-order formulation. Schanuel's conjecture says that if some Z complex numbers Zi are linearly independent over Q, then the Zi's and the e to the Zi's as a 2n tuple do not lie on any algebraic set V of dimension less than n defined over Q. The uniform version says that given such a V, any such points on it are essentially accounted for by finitely many possibilities for the rational relations on the Zi's. The additional content of the uniform version is just what Zilber-Pink asserts in this setting. The exact form which I've put up there is a little technical and is not important for us. The point is that the model theory of complex exponentiation is one source for this Zilber-Pink conjecture. O-minimality, on the other hand, grew from a question of Tarski concerning the model theory of real exponentiation. The real exponential doesn't oscillate, so it doesn't look like you can define the integers, and one could expect or imagine that its theory is very well behaved. So that was behind Tarski's question. In the 80s, Van den Dries considered a certain finiteness property of definable sets, which we'll see in a minute, in the context of real exponentiation, and Pila and Steinhorn developed the theory in general. The O-minimality of real exponentiation was proved by Alex Wilkie in the 90s. So we consider now first-order structures consisting of the real numbers with their field operations and with the order relation, and this is to be extended by the addition of some other functions or relations, the fi's and the rj's. And in this theory, it doesn't matter whether you add functions or whether you add their graphs as relations. It somehow makes no difference. And definable sets in the structure are those sets which have a definition using the given functions and relations, real parameters, logical connectives, and quantifiers over R. And I've just written down one example that was as long as I could get on the line. Now, such a structure, that's a very general object, such a structure is called O-minimal if all the definable subsets of R are finite unions of points and intervals, possibly unbounded. So this, for example, this fails if one of your functions was the sine function because its zero set doesn't have this form. And the motivation is that such sets are already definable just with the order relation and real parameters. So the addition of these further functions and relations has not resulted in any new definable subsets of R itself. O-minimal stands for order minimal. Of course, there will in general be new subsets of R squared, and so on. Pila and Steinhorn proved the fundamental cell decomposition theorem from which strong uniformity properties of definable sets in O-minimal structures flow. The two key points for us are, firstly, that the definable sets in such a structure satisfy very strong tameness conditions. For example, a definable function must be continuous except at finitely many points in its domain, also differentiable. And in a definable family of definable functions, the number of points of discontinuity or non-differentiability is in fact bounded uniformly over the whole family. So these are very strong properties. And secondly, that nevertheless some quite rich structures are indeed O-minimal, and in particular the structure you get by adding real exponentiation, as proved by Wilkie, as well as was proved later, adding arbitrary restrictions of multivariate real analytic functions restricted to compact boxes. All right, so now I can turn to point counting. Counting solutions of some Diophantine system up to a given height is a well-traveled path in Diophantine geometry. For example, it is believed that there is no positive integer that can be written as a sum of 2/5 powers of integers in two different ways. The corresponding equations, which I've written there, have of course plenty of trivial solutions, which you get by using the same pair of integers on each side of the equation. And what is known by counting methods in this case is that asymptotically there are fewer non-trivial solutions than trivial ones up to some large height t. The trivial solutions correspond to lines in the corresponding algebraic variety. And note this variety is not a curve. And the current knowledge for higher dimensional algebraic varieties, the knowledge about Diophantine properties, is much less developed and complete than for curves, where we have Mordell's theorem, though there are far-reaching conjectures of Bombieri and Lang. Motivated by some questions raised by Peter Sarnak, Bombieri and I wrote a paper some 25 years ago concerning rational points on plane curves. We proved results in various contexts: algebraic curves, smooth curves, real analytic curves, and they asserted that under certain natural hypotheses, there could only be few rational points on these curves up to a given height. The method used was elementary real variables, and it depended on the fact that given a positive integer d on such a graph, rational points of small height, which are too close together relative to the size of the function and some of its derivatives, must lie on an algebraic curve of degree d. And this is because the determinant which controls this is too small for its height. A rational number of height less than n and size less than 1 over n must be 0. Later, Heath-Brown proved results for rational points on algebraic varieties of arbitrary dimension, counting results, using a p-adic version of this determinant method. And this raised the question of using the original real variable method to study rational points on higher dimensional sets defined by analytic conditions. Alex Wilkie and I proved a general result for sets definable in an O-minimal structure over the real numbers. So these include all bounded analytic sets, for example, but they in fact include their more generality that turns out to be crucial in the applications. So one thing we have to allow now, when you look at higher dimensional sets, we must allow for the fact that such sets may contain algebraic subvarieties, even if the set itself is transcendental. For example, the non-algebraic surface z equals x to the power y contains infinitely many algebraic curves, which you get by setting y to be a rational number. And so the result refers to the transcendental part, what we call the transcendental part of a definable set, which is the set deprived of all connected positive dimensional algebraic curves that may lie inside it. And the union of those we call the algebraic part of the set. And as before, rational numbers, we count them by their height. The height of a rational number is the maximum size of its numerator and denominator when it's written in lowest terms. And on an n-tuple, we just take the maximum height over the coordinates. So the basic result is then as shown. It says that if you remove the algebraic part of any definable set, then you get very few rational points. And the very few here is an estimate of the shape of some constant, depending on your set, an epsilon, t to the epsilon, for any positive epsilon. So I won't say anything really about the proof of this theorem, except that O-minimality enables the underlying elementary idea to be iterated. And this requires an O-minimal version of a parametrization theorem proved in the algebraic case by Yomdin and Gromov around 1987 for quite different reasons. And the uniformity aspects of these parametrizations are what's crucial. And I also want to observe that one can prove a result of the same quality for algebraic points of bounded degree. For example, points whose coordinates are all quadratic, where now the height is defined by the coefficients of the minimal polynomial in integer form. And we will need this. All right. So finally, we come to the Diophantine applications. Umberto Zagna suggested that the counting theorem could be used to give a new proof of the Manin-Mumford conjecture, Raynaud's theorem. And he also saw that the same idea could be used for some relative Manin-Mumford problems that he was working on with David Massa, and he described some of these and their applications yesterday. The generalization of the counting theorem to algebraic points of bounded degree and the analogy between Munn and Mumford and Andre Oort conjectures suggested attempting the same strategy for the latter problem. In fact, all the special point problems have the same general form. The ambient variety X has a uniformization by suitable transcendental functions defined on some complex domain. For C star to the n, it is just the map from C to the n given by the exponential function on each coordinate, which I have normalized here for a reason which will become apparent very shortly. And for C to the n, as a Shimura variety, it is the map from h to the n, the nth power of the upper half plane, given by the j function on each coordinate. And I'm going to assume for simplicity that the subvariety v is just defined over q. Now, the full graph of complex exponentiation, considered as a subset of r to the fourth under the identification of c with r squared by real and imaginary parts, say, is not definable in any O-minimal structure due to its periodicity. And the same holds for the full graph of the j function due to its invariance under the modular group. But in both cases, the restriction of the map to a fundamental domain for the action by z to the n, or SL to z to the n, is definable in an O-minimal structure. That's the structure which is called Rnx. So this gives the first key ingredient. In each case, the pre-images of special points are algebraic points of bounded degree in suitable real coordinates. For the exponential function, as normalized, they're in fact just rational points. And for the j function, they're quadratic points. So instead of studying special points in V, we may study rational or quadratic points in this definable set Z, obtained by intersecting the pre-image of V with a fundamental domain. Now, what happens is that if V contains a torsion point or a special of order, so that was my next slide. Sorry, I had one more remark here. So instead of studying the special points in V, we can study rational or quadratic points in Z, and this set Z is definable and in general very far from algebraic, because it's defined by algebraic conditions on the e to the zi's or the j of zi's. So the next crucial ingredient is that special points down in X have large degree over Q. And continuing with example 1, a root of unity of order n has nearly n Galois conjugates over the rational numbers, while its pre-image in the standard fundamental domain is a rational point of height n. So this means that if V contains a torsion point of order n, and hence also its Galois conjugates, then our definable set Z contains nearly n rational points up to height n. And this is to be compared with an upper bound for such points on its transcendental part of the shape C of epsilon n to the epsilon for any positive epsilon. So if we take, say, epsilon equals a half, we can see that all but finitely many torsion points must lie in the algebraic part of the corresponding definable set. And to complete the proof, we must characterize this algebraic part. The answer is given by the Ax-Lindemann statement for the map E. Maximal algebraic subvarieties in the pre-image of V have a particular form. they're translates of rational linear subspaces, which we have called weakly special, and their images are cosets of subgroups. So this gives finiteness of isolated special points, and for positive dimensional weakly special subvarieties, one uses an inductive argument to give a new proof of this multiplicative Manin-Mumford statement. So now we are going to replay exactly the same proof for the J function to prove the André-Oort conjecture for C to the n. Ingredients 2 and 3 are arithmetic results that come from the classical theory of complex multiplication of elliptic curves initiated by Kronecker in the late 19th century, and from the Landau-Siegel lower bound for the class number of an imaginary quadratic field. The complexity of a special point in C can be measured by its discriminant. By complex multiplication, a special point of discriminant delta has degree equal to the class number of the corresponding quadratic order. By a result of Siegel, the size of the class number is almost the square root of the size of the discriminant, with an ineffective constant coming from possible counterexamples to the generalized Riemann hypothesis. And the corresponding point tau, however, in the fundamental domain, in the product in the upper half plane, has height simply about the size of the discriminant. And this means again that if our variety V contains one special point of large discriminant, then the definable set Z contains too many quadratic points, and they must lie in its algebraic part. The last ingredient needed is the Ax-Lindemann theorem for the modular function, which characterizes the maximal algebraic subsets in the preimage of V. While the exponential case of Ax-Lindemann is a special case of the original result of Ax and is proved by differential algebra, the proofs of the corresponding result for Shimura varieties proceed in the complex setting with further use of O-minimality and the counting theorem. And then you have again an inductive argument to somehow deal with higher dimensional things. So I can see I'm taking up too much time. I want to mention just briefly somehow further progress on André-Oort. Ulmo has shown that with these 4 ingredients for a Shimura variety X, one can indeed establish the André-Oort conjecture by this method. Every Shimura variety somehow has a transcendental uniformization by a suitable complex domain. The preimages of special points are always algebraic points of bounded degree, so you always are somehow in shape to apply this method. And then if you have these various ingredients, you can complete the proof. 1 and 4, definability and Ax-Lindemann are now in fact known in all cases, and ingredient 3 in some cases. And the main lacuna to a full result are the Galois lower bounds, and they're known for the moduli spaces up to dimension 6, the result of Jacob Zimmermann. And yeah, so well, I guess I'll just finish on this note that more general problems of atypical intersections can also be approached by O-minimality in point counting, because special subvarieties are defined by rational or bounded degree conditions. So there are various results by various people which have been obtained, and one expects suitable versions and results more generally. I guess my overall message is that we have here a very rich collection of problems in arithmetic and functional transcendence revolving around Ax, Schanuel, and Zilber-Pink, and which both grow out of Schanuel's fundamental conjecture. So, thank you very much.
Thank you for this beautiful account. Are there questions? Well, if not, let's thank Jonathan again, and he gets a gift.
Thank you.